Okay, so I will give lectures on general relativity, so they are introductory, and I apologize in advance to many of the people here in this room who are specialists. But in any case, at least for this first course, I'll try to give a sort of a presentation which is historical and which tries to sort of clarify some of the main issues in the theory. So with this, let me start. First of all, I want to discuss a little bit about the relationship between mathematics and physics. In particular, I'd like to emphasize that somehow the subject that we are interested in is mathematical general relativity, and this is something that needs a definition. So let me start by saying that, fortunately, I guess it's hard to both be here and have control on the screen, but maybe I'll do it this way. So mathematics is relevant to physics in two distinct ways. First of all, it provides a language and tools to formulate new physics. As an example, of course, you have Newton, who uses analytic geometry, uses geometry and calculus in order to develop the law of mechanics. You have Maxwell, who uses a language of partial differential equations to formulate electrodynamics. You have Einstein, who uses a language of Riemannian geometry, which was developed by Gauss and Riemann. All these people who are all these relations, of course, are relations between things which were developed by mathematicians before and then used by physicists. Heisenberg uses a language of linear operators in Hilbert space to formulate matrix mechanics. And of course, Schrödinger, who finds a PDE formulation of quantum mechanics based on the Hamilton-Jacobi theory. All right, so this is one way in which mathematics is relevant to physics. Here is a second way, which is that mathematics starts with the physical theory, and then it develops the consequences of the physical theories, right? So, so geometry, of course, is the first such example, because Euclidean geometry could be viewed, starting with Euclid, formulated by Euclid, could be viewed as sort of a formulation of the axioms of geometry of physical space. And therefore, in that sense, it is really the first physical theory that we had. Becomes an essential part of mathematics. Of course, it is developed, and here is a primary example of a physical theory developed for centuries as a pure mathematical discipline without any or very little new input from the physical world, but which grew nevertheless to have deep, mysterious, and completely unexpected consequences, to the point that physicists talk of a complete geometrization of modern physics. So another example, of course, is the development of mechanics after Newton. Once the Principia appears, mechanics is developed not only with a view towards specific applications, but also with a goal of understanding and expanding the formal mathematical aspects of the theory. This leads to the revolutionary Lagrangian and Hamiltonian reformulation of Newtonian mechanics, and new mathematical subjects such as calculus of variations, Hamiltonian dynamical systems, symplectic geometry. So this is clearly an example that we all know of huge impact of mathematics on the development of an established physical theory. Here is another example, but of course there are millions. But Fourier initiated, so the Fourier analysis was initiated in works by D'Alembert, Euler, and Bernoulli, in connection to the study of the one-dimensional wave equation, the vibrating string. So Bernoulli's daring idea of approximating general functions, periodic, by sums of sines and cosines was later developed by Fourier in connection to the heat equation. And of course, this had a huge impact on many, many branches of applied sciences and theoretical sciences. Okay, so again, to review, mathematics is relevant to physics in two distinct ways. It provides a language and tools to formulate new physics. It develops the consequences of the established physical theory. And of course, there are plenty of examples on both sides. I should say also that even two can be viewed as different from one. Very often, somehow the development of tools connected to his previous physical theory lead to reformulations, like it happened in the case of Newtonian mechanics, which later feed back into physics through one, right? So it provides a language for something new. And of course, again, there are plenty of examples, and I'd be happy to discuss more if people want. In any case, as a corollary, and this is the point I wanted to make, is that we should envision the established physical theories, such as general relativity, as integral part of mathematics, and to develop them on pure mathematical terms, asking questions we consider fundamental, which may not coincide at any given moment with those physicists are most interested in, and providing, of course, full rigor to our proofs. Okay, so that's sort of, if you want, that's what mathematical relativism is all about. It's something that has roots, deep roots in physics, but we try to develop on mathematical terms. Right. So that's that was an introduction in what I call mathematical general relativity. Now let's talk about various aspects of general relativity. First of all, causality in Lorentzian geometry. So of course, Lorentzian geometry is based. So you have to interrupt me. Well, let's see. How many people here are really beginning students who don't know that much geometry? Probably nobody, right? So is there anybody who I see only expert faces, maybe one. Okay. Okay, so I can go fast. So view it as just a review of basic things in general relativity. Anyway, causality, of course, starts with the definition of a Lorentzian metric, which is, unlike a Riemannian metric, is not positive definite. And but then, of course, the basic concepts in Riemannian geometry also apply to Lorentzian geometry. The only difference is causality. So causality is something that you don't have in Riemannian geometry. Of course, vectors are time-like, space-like null. And I'll have a picture of this. Curves also can be time-like, space-like null based on the tangent to the curve being a vector of those three types. We can have hypersurfaces, and then you identify as being space-like, time-like, or null, depending on the normal to the hypersurface. And here is a nice quotation from Henri Poincaré. You have it in French, but I have it in English also, for those who don't know French. Anyway, it's sort of a beautiful sort of understanding that Poincaré had very early on, that somehow Lorentzian geometry really leads to a new kind of geometry also, which is still in some sense positive definite, but it's not Riemannian, and it's not of the type of Lobachevsky and Riemann or Euclid, and that has to do with null geometry. So of course we all know that on a null hypersurface, the metric induced on a null hypersurface is not positive definite in the traditional sense. And here Poincaré quotes a result. So this is in English. Poincaré quotes a result of this new geometry, which is called null geometry. We call it null geometry. And the theorem in this null geometry is that you can have a line which is perpendicular to itself. Okay, so that's kind of strange, but that's typical to the geometry induced on a null hypersurface. All right, so let me go on. Null geodesics, of course, we know what they are. So they represent geodesics, which are also null in that sense. Here is a causality in Lorentzian geometry. The important things, the important new concept, of course, is that you can have past and future sets of points and sets. So in this case, of course, the causal future of a point in Lorentzian geometry are all those events which can be, or all those points in space-time, which can be connected to the point to start with by time-like or null curves. And here, this represents the future of a set S. In other words, it's not just the future of a point, but the future of a set of points. And you can see here the future represented in gray, and then the boundaries, and so on and so forth. So you get all sorts of very interesting features of causality. The boundaries, of course, are null. Everything at 45 degrees, of course, is null. All right, so let me go fast over these things. Here is another important concept in general relativity, which is that of global hyperbolicity. So associated with global hyperbolicity is the notion of a Cauchy hypersurface, right? So a Cauchy hypersurface is a surface such that every point, if you look at every point, say, to the future, you can define the notion of future and past. Every point can be any time-like or null causal, I should say, curve which passes through this point will intersect this hypersurface sigma 0 at just one point. Okay, so that's what a Cauchy hypersurface is. So, for example, here you have a Cauchy hypersurface. The interior of this ball is a Cauchy hypersurface. If you take the ball, if you take this point, however, away, so in other words, without this, so maybe I should look here. So without this, this is a Cauchy hypersurface for this region. It's not a Cauchy hypersurface for this region. And of course, even for this region, if I take a point away, then it's not a Cauchy hypersurface either, because this curve, this time-like curve, does not intersect. So this is an artificial way of taking points away. Anyway, and of course, the global hyperbolicity is just a statement that if you have a manifold Mg, it must have a Cauchy hypersurface. Okay, so in other words, a hypersurface which has these global properties. Okay, so here is another important concept, which is domain of dependence. So that the domain of dependence on this set corresponds on all these points, which can be connected by time-like or causal curves to S1 in the future of S1. And of course, again, you can see that if I take a point away, this future domain of dependence looks now rather strange, because you have to take away all this region now. And you get the boundaries of the sets will include, so the boundaries will include what is called Cauchy horizon. So Cauchy horizon in general relativity is a boundary of a future set of a point, or the future set of the point S1 or domain of dependence are one and the same thing. So domain of dependence is used by people in PDs. Causal futures and past are usually very familiar concept in relativity. Okay, so let me go on. So let's talk about now a little bit of intellectual history of the subject. So first of all, obviously we have Galileo Newtonian laws of classical physics, Newtonian gravity, which were formulated a few hundred years before. We had, as an important step, the Euler-Lagrange reformulation of Newtonian mechanics, which of course was immensely important in later developments of physics, even though clearly this could be viewed as a mathematical development of the subject, which was, I mean, of the theory, which was introduced by Galileo and Newton. Right? So this goes under the example 2 that we discussed earlier of impacts of mathematics into physics. We have the Faraday-Maxwell laws of electromagnetism, which of course were formulated in the 19th century. By mid-19th century, you had Maxwell equations. We had Gauss and Riemann foundations of Riemannian geometry, with important contributions by Ricci, Bianchi, and Levi-Civita. So of course, this obviously is essential for the formulation of general relativity by Einstein. By 1900, the main physical theories were, on one hand, Newtonian mechanics. And at the heart of Newtonian mechanics, of course, as we all know, there are these Galilean transformations, right, which move space and time according to this. And of course, time is absolute in the sense that time it does not suffer any non-trivial changes. Of course, in the Maxwell equations, as discovered by Lorentz, the equations are invariant not relative to this. So, of course, Newtonian mechanics is invariant relative to these transformations. Electromagnetism is invariant under a new group of transformations, which was discovered by Lorentz. And, of course, these are Lorentz transformations. And, of course, a remarkable thing at the beginning of the 19th century is that these two things were very different. So you had these two incompatible theories, one which is invariant under this one is invariant under this. And it's exactly this incompatibility which led Einstein to formulate his special relativity. So special relativity is nothing else but saying that this is wrong and this is good. But then, of course, you have to somehow understand in what sense this is tied to this. And, of course, it's tied because if you take c to go to infinity, you get this, right? So in the limit, as the speed of light goes to infinity, you get from special relativity, you get from Lorentz transformation, you get Galilean transformation. And special relativity is nothing else but this. Okay? So special relativity is just this understanding that this is more fundamental than this, and that you take this as axioms. Of course, this leads to E equal mc square law. It leads to all sorts of remarkable things. The next big development was the one of Minkowski and Poincaré to some extent, which both of them understood that somehow behind this Lorentzian transformation, behind special relativity, is a new type of geometry, which is not Riemannian anymore, but the time comes up with a minus sign in front of it. Okay, so that's what Minkowski understood. So Minkowski reformulated all special relativity in terms of this. This is the geometric framework of general relativity, right, where you have time and space, but the time can change. You can rotate the time. For example, if you look at this light cone, the direction of time can be taken any place you want in this light cone. And as a consequence, the surfaces of simultaneity will differ. Right? So that's why simultaneity is a relative concept in relativity. It's not an absolute concept, not an absolute anymore. So simultaneity, you have the new notion of proper time. You have an extremely important synthesis between velocities and momentum. Between the space-time velocity and the momentum, which is the four momentum. You have electromagnetism in this new setting of Lorentzian geometry, or Minkowskian space, if you want. All the laws of electromagnetism achieve incredible formal elegance. And you can see it here in this new slide. You have the Maxwell equations written by Maxwell. Actually, even Maxwell wrote it even worse than this, because instead of having a curl, he wrote down all the components by hand. So you had you have to fill a whole blackboard to write down all the equations. In any case, in modern vectorial notations, it's written like this. But of course, if you use the formalism of Minkowskian geometry, then the electromagnetic field, which is a combination of B and D, the electric and magnetic field, they can be put together as a two-form. Right? This is a dual, the Hodge dual of the two-form. And the components of F relative to space-time indices, space and time indices, are nothing else but the E and B that you have here. So as you see, E and B are both synthesized in this two form, which is a space-time two form. The indices here, of course, I mean, the usual standard notation I'm using, which is the indices alpha and beta go from 0, 1 to 3, right? So this is beta is 0, 1, 2, 3. Of course, the Minkowski metric itself is like this, d x alpha dx beta. Right, so I'm using obviously the summation convention, so this is a sum. And of course, alpha and beta are running from 0, 1 to 3. 0 in some sense corresponds to time, and this corresponds to spatial boundaries. All right, so again, for most people here, this is familiar. In any case, you see now that the Maxwell equation takes this very simple form. So it's a divergence. So all these four equations can be expressed in terms of just this and this. This is the exterior derivative of f. And the other one is a divergence equation. Okay? We'll see that again later on when we discuss the variational properties of the Maxwell field. Okay, so that's, these are the Maxwell, the vacuum Maxwell equation, the Maxwell equations in vacuum. In other words, if I don't assume the presence of any G and ρ, which correspond to a current in the theory, in that case, you see the equations take this very simple and very symmetric form. So df, this is just exterior derivative, right? The standard exterior derivative of a two form. And this is a divergence operator, right? And relative to a Hodge dual, it's remarkable that if you take the Hodge dual of this, you get this for the corresponding Hodge dual, and vice versa. So there is this incredible duality between D and delta, which obviously you would never be able to see in this context. So there are all sorts of new things that come because you interpret the equations in this special relativity framework. Okay, so a little bit the birth of general relativity. Again, I'm going to go very fast, but I just wanted to say that the original laws, the classical laws of gravity look like this. You have a potential here, Laplacian of I, is equal to 4 pi rho. Rho is the density of mass, so you have sort of imagine that you have some mass, right? Rho is density, and this is the motion of point particles under the influence of the mass, right? So you have a point particle here which moves attracted by this mass, and the equations look like this, right? So the potential generated by this volume of mass of density rho is given by this, and then the point particles move according to this equation. So this was Newton's law formulated in this way, and of course Einstein, you can see him here. He was trying very hard to see how this could be put on a Lorentzian basis. He was in Bern, a beautiful, beautiful place. I guess he was younger than this, but never mind. And finally, he gets this incredible idea, which he calls the happiest thought of his life in 1907. And here, this is in his own words. I was sitting on a chair in my pattern office in Bern. Suddenly, a thought struck me: if a man falls freely, he would not feel his weight. Right? So this leads to the principle of equivalence. So using simple thought experiments, he deduces the gravitational time dilations and the deflection of light, just based on this, and of course using special relativity. And one cannot, in principle, construct inertial observers in the sense of special relativity to measure the gravitational force on a test particle, not text particle, test. But of course, he immediately realized that such inertial observers can be envisioned as freely moving along geodesic in a curved spacetime. Of course, by that time, he didn't have even the concept of a curved spacetime. He was, in fact, even though Minkowski was his teacher, as we all know, he didn't pay much attention to Minkowski's reformulation of special relativity. He thought that was a mathematical sort of funny thing that is not too important, just what mathematicians do in their spare time. But of course, now he realizes that actually it's exactly these sort of things that are extremely important. And he goes on, by 1912, 1913, he deduces that if all our accelerated systems are equivalent, then Euclidean geometry cannot hold in all of them. So this is the beginning of his understanding that you need geometry, and you need something like Riemannian geometry. Together with Grossman, whom you see here, he begins to incorporate the. So Grossman was a mathematician, of course, and it's to the tribute of Einstein that he realized that he's missing something very important, which he should have learned maybe when he was a student at ETH, particularly from Minkowski, but he didn't. And anyway, he's now very hard studying this, and he studied the works, of course, of Riemann, and then also the Ricci, Levi-Civita. And here is what he says. In all my life, I have not labored nearly so hard, and I have become imbued with great respect for mathematics, the subtler part of which I had in my simple-mindedness regarded as pure luxury until now. Right? So this is a nice tribute to mathematics. All right, so anyway, so there are future developments. Nordstrom in 1913, he tries to find a theory which looks like this, where you take the metric to be just proportional to the Minkowski metric, so you have just a scalar here. Then the Ricci, the scalar curvature of the metric looks like this, is GAV times T alpha beta. This is the energy momentum tensor. We'll talk more about this later. Anyway, I just want to give you sort of a glimpse of what Einstein was going through. In 1913, Einstein abandons an approach based on general covariance. So general covariance is, of course, what we know about general relativity is a general covariant theory. However, he himself sort of gave up on that in 1913, only to come back later, a year later, to realize that this leads him to an incorrect version of GR. And another year, it takes him another year to return to an approach based on general covariance, right? So finally, in 1915, and this is exactly 100 years ago, minus a month, but that's why we are all here, I guess, because of this. So he writes down the true equations. That we know them as Einstein field equations. And of course, he had a correspondence with Hilbert. There was some go back and forth with Hilbert. Hilbert actually had apparently the same equations. He had published them 5 days earlier. So using a variational approach, which in fact Einstein also uses in the end. His original derivation was more physical, but the final derivation, and the derivation of the correct equation was variational. Okay, so let's in fact talk about a little bit of the variational principle, right? So again, the space-time is the main new object. It's a manifold together with a Lorentzian metric. So that's a space-time. You have a collection of fields in the space-time. So besides the metric, you can have various fields, in particular, for example, an electromagnetic field, right? So psi can be, in fact, this F alpha beta, which is an electromagnetic field. But you can have many fields. You can have scalar equations. You can have matter fields, and so on. You have then a Lagrangian density. So the Lagrangian density is, of course, what defines the theory. So I should say, again, this is one remarkable fact about the impact of mathematics on physics, is that most modern physical theories come with just writing what a Lagrangian is, right? And of course, Lagrangian, I mean, the Lagrangian was sort of this incredible reformulation of the laws of mechanics, which was established by Lagrange essentially at the end of the 18th century, beginning of the 19th century. And this seems to be, I mean, the physicists don't even bother to write down the Euler-Lagrange equations. They just write down the Lagrange density, the Lagrange and the action, and then they do something that's supposed to be quantum mechanical and so on and so forth. Anyway, I'm not going to get into this, but I just wanted to say, so you start up with a Lagrangian. So every physical theory that we are going to talk about are defined like this. You take a Lagrangian, which of course will depend on the metric, depends on its inverse, and depends on this size. Then you associate to them an action. So Lagrangian, of course, it's extremely important to say that the Lagrangian is a scalar quantity. So it's a scalar quantity which is formed with tensors, right, which are far from being scalars. So there are tensors and tensors. You form a scalar, and then you integrate the scalar, and that gives you the action. Here is a volume element corresponding to the metric. Again, I'm going fast because I feel that if it's just one person who doesn't quite know these things, I have to go fast, right? So if I hear more voices, people telling me that I should go slower, I will go slow. No? No taker? Okay, I'll go fast. All right, so okay, so the action, therefore, is an integral of the field, right? Now, in what I'm writing now, I take variations just only of psi, right? So you could also take variations of g, which we'll discuss it in the next slide. But for the moment, imagine that you fix the g and you take variations of psi, right? So this is what a variation is all about. Okay, so it's just a continuous deformation of psi here, right? Such that when s is equal to 0, you get the original psi, the psi you want to start with, and psi is also equal, psi s is equal to psi outside the compact set. And finally, psi is said to be stationary if the derivative of the action relative to s at s equal to 0 is equal to 0, right? So that's what identifies the Euler-Lagrange equation. So if you do this, you get the Euler-Lagrange equation. The action principle, of course, says that any acceptable solution of the physical system must be stationary with respect to a given Lagrangian density, right? So that's how essentially every physical theory that we talk about, how it is derived. Right, so you have the Euler-Lagrange equations, which are obtained simply from this variation in each particular case. Okay, so now for the Einstein field equation, it also has a Lagrangian, but now the Lagrangian has to depend on the metric, right? So this is called the gravitational Lagrangian. So there is a Lagrangian here, which is a total Lagrangian that has a gravitational part and a matter part. So M stands to matter, right? So M stands to, for example, to the Lagrangian corresponding to F, which we'll write down in a second. And the remarkable thing about Einstein's theory is that the Lagrangian is taken to be a geometric invariant. So it's nothing else but so as we know, if you have the metric, you have the Riemann curvature tensor, right, of the metric, which is a complicated expression involving second derivatives of g. And then you can form the Ricci curvature by just taking the trace relative to two indices. And then again, you can take another trace and you get the scalar curvature. So this is what you plug it in here. This is a scalar curvature. Sorry, for the Lagrangian of the gravitational Lagrangian, you take it to be just a scalar curvature, nothing more geometric than this. right? So, and then now you perform a variation both of the metric, right? So now you do exactly the same thing on the previous slide, but you vary both the metric and the size. So if G was fixed and I vary just this, so I get the equations which are like the Maxwell equations or the equations of motion of fluid and scalar equation and so on and so forth. But now I'm varying both, so I have to get something interesting. So the variation corresponding to just the metric, if I vary just the metric, what I'm going to get is the variation of the scalar curvature, which I'm writing it here, plus the variation of the volume form. Okay, so I mean that's very easy. I mean you just look at R integral of R dvg, right? So this R depends on S through the metric, and this depends on S. So if I differentiate, I'm going to get differentiation of this plus differentiation of this, right? So just Leibniz formula. So this is a Leibniz formula. And then if you work it out, you find that the dvg, so in other words, the variation of the volume, can be expressed in terms of variation of the metric in this form. So you take the trace of the variation, and you get back the volume, right? So this g dot mu nu is just the variation, in other words, the derivative of g with respect to s, evaluated at s equal to 0. So if you then you write down what this is, it's very easy to see. So this requires a little bit of a calculation, but it's not a hard calculation at all. It's very easy to see that these two combined give you this. Right? Okay, anyway, so so at the end of the day, there was a mistake here, I think. Yeah, no, I think what I wanted to say. Anyway, what I wanted to say is just the gravitational part. So I think this part, there is something there's something wrong about this. But anyway, let's forget about this part. So this is correct, and this is also correct. At the end of the day, this is what you get. You get the variation of the action corresponding to the gravitation is given by this tensor. So this is the Ricci curvature whose index is up, minus a half the Lorentz metric whose index is up, g mu nu times the scalar curvature multiplied by the variation of g. Okay, so that's that part. Again, that's a very simple calculation. It just takes a few lines. Today, at least. I guess it took Einstein a lot longer. If you take the derivative of the matter Lagrangian, then you get something like this. Let me not write down all the details. The important thing is that at the end of the day, if I take d over ds, I'm going to get the derivative of the Lagrangian with respect to the metric minus a half g mu nu times the Lagrangian multiplied by g dot mu nu. Okay, so this is not too difficult. I mean, obviously, the Lagrangian, let's look at the specific Lagrangian just to see it easier, see what happens. So I look at the specific Lagrangian. For example, the Lagrangian associated to a scalar field. So this will be the manifold. So it's 1 plus 3. So we are in 1 plus 3 dimension. There is a metric. And this is a map into R, let's say, the simplest case. And the Lagrangian is just g mu nu d mu of I d mu of I. And in this situation, I'm only varying the Lagrangian, the part of the Lagrangian that has to do with g, because it's only g that is being varied here. The variation, sorry, there should be a phi here. The variations with respect to phi, I do it separately, right? These are the variations with respect to the matter. But if I do the variation with respect to the metric, then obviously this Lagrangian will, of course, be also differentiated with respect to S, right? So when I do that here, I get I get the derivative of the Lagrangian with respect to the metric multiplied with a variation, plus the Lagrangian itself multiplied with a variation of the volume form, because again, the action is given by the Lagrangian, which is this one, multiplied by dVg. Okay, so obviously when I vary, I have to vary both of them relative to g, and this is what you get in the end. You get the derivative with respect to g minus a half g mu nu times Lm, and this is what is called the energy momentum tensor. So this is something very important, extremely important quantity, is the energy momentum tensor of matter. You see, it's whatever you obtain when you take variations, but of the Lagrangian, right? But the variation is done only relative to the metric itself, right? So what you get in the end is that this is equal to this, right? G dot, the variation is arbitrary. So as a consequence, you get the Einstein field equations, which is at the left-hand side. On the left-hand side, you have just the Ricci minus a half g mu nu times scalar curvature is equal to T, which is on the right-hand side is the energy momentum tensor of matter, of all the matter fields, right? Because you can have lots of matter fields, and which is defined simply like this, right? So you see it's a very, very simple calculation. For example, in this case, you get, if I look at the energy momentum tensor associated with this, it's very easy to see that you get just d alpha of phi, d beta of phi, minus half g alpha beta times g mu nu, d mu of phi, d mu of phi. Right? So this is the standard energy momentum tensor of the scalar wave equation. Right? So it's always extremely easy to calculate what the energy momentum tensor is from this point of view. All right, so that's these are the equations. Again, the same one as here. But now here it's a remarkable thing happens, which is one of those mysterious facts about the Einstein equations. You see, the energy momentum tensor, the whole point about the energy momentum tensor of this, for example, this is just a wave equation. So the Euler-Lagrange equation, Euler-Lagrange means I do the variation with respect to phi, not with respect to g. So if I vary just the phi, I get the wave equation. And this one is the energy momentum tensor of the wave equation. And you know, a fact that everybody knows about an energy momentum tensor is that it verifies a divergence equation. The beta of T alpha beta is equal to 0. So these are the laws of conservation, local law of conservation of energy momentum tensor. And this you can just check. It's very easy to just check. It has nothing to do with the Einstein equations. It's just a fact about the wave equation. The metric is fixed. I don't have to vary the metric. And the remarkable thing is that somehow, if you just look at this part, and you look at the Bianchi identities. So the Bianchi identities are general facts about a metric. If you take cyclic permutation of these indices, you get 0, right? So you take the Riemann curvature tensor, and you take covariant derivatives, and take cyclic permutation over 3 indices, you get 0. This is just a general fact of Riemannian, Lorentzian, it doesn't matter. Now, if you use that fact and you contract twice, you have 5 indices here, now you contract and you get only one index at the end. If you contract, you get that d nu of this quantity is equal to 0, which means that d nu of this quantity should be equal to 0. So you get the laws of conservation, the general laws of conservation of energy momentum tensor just from geometric properties of this. So this is one of the remarkable things about the Einstein. This is maybe the one thing that Einstein was most impressed with, because in some sense it tells you that the geometry tells the matter how to behave. Okay? So the geometry of the metric has these remarkable consequences of the behavior of matter. Anyway, so this is Now, obviously, in addition, so here I wrote only what you get by doing the variation with respect to the metric. But if you do the variation with respect to psi, you get the usual Euler-Lagrange equation of the matter field. So, for example, if you consider a space-time together with G and the scalar field phi, and you do this procedure, you are going to get R alpha beta minus a half G alpha beta. So this is the Einstein tensor is equal to, on the right-hand side, the energy momentum tensor of phi, of this phi, right? Which is exactly this, okay? Right? And so this is just the first part of the Einstein equation. Now the second part is a variation of the Lagrangian of matter, which is in this case is phi, relative to phi itself, and you get 0. So you get an aversion of phi 0. Okay? So the coupled equations between the Einstein, between the metric and the scalar field are these two. Okay? So it's very, you see, it's very easy to derive. And of course, it's a non-trivial coupling because obviously you solve the phi, you need the G, but then if I have a given phi, so for a given phi I solve for phi, I solve for a given G I solve for phi, I plug it in here, but then I get a new G which I have to plug it back here. So it's a coupled system. It's a complicated one, but these are exactly the sort of thing that mathematical theory of general relativity should study, right? This kind of complicated couplings. Okay, so this is a Lagrangian of the scalar wave equation, which I just wrote. Then, for example, the Maxwell equation, the Lagrangian for the Maxwell equation is right, so the electromagnetic field is given by a 2 tensor, and the Lagrangian is given by F mu nu, right, with a convention of raising and lowering indices relative to the metric. So this, in fact, is F mu nu, F alpha beta, G mu alpha, G nu beta, right? So that's a scalar quantity which is obtained with F and the metric. So this is, if you vary these equations, we'll do it later, but if you vary this equation, you get the Maxwell equation. So by varying, I mean variation, of course, with respect to F. All right, so, okay, so scalar wave equation, this I just wrote. This is what the energy momentum tensor looks like. We just did it on the board. This is, if this is the Lagrangian of matter for the Maxwell equation, then the energy momentum tensor, it's easy to calculate. You get this. It's the same calculation as here. The general properties of the energy momentum tensor is T symmetric. This is by definition, the way it's defined, it has to be symmetric. It's a variation with respect to a metric, which is symmetric. The metric itself is symmetric. T is divergent, as we just saw. It follows from the Bianchi identities, the twice contracted Bianchi identities. But another important thing, which is not easy to read from the theory at all, is that positivity. So good energy momentum tensor of matter, so good matter, in other words, should satisfy the positivity condition. Namely, if you take a 2 tensor, you can always contract it with 2 vectors, 2 vector fields. And this quantity should always be positive if the vectors x and y are time-like and both future-oriented, future or past-oriented, but of course we always talk about future-oriented. Okay, so main features of the Einstein field equations. Now, how much time do I have? Maybe we should take a break at some point. Is there okay. Okay, in a few minutes. So maybe I can still talk about this. All right, so as you see, I want to give you sort of a broad view of the theory, and that's why I'm going to go through all sorts of things. Right now, I want to talk about the main mathematical features of the equations, of the Einstein equations. First of all, they are generally covariant, right? So covariant means simply that everything is expressed in terms of tensors, and all the differential equations are expressed in terms of covariant derivatives of a given metric, right? So there is a metric and tensors. That's all that is to it. Metric, tensors, covariant derivatives relative to the metric. All the equations are expressed only in terms of these quantities, and there is nothing more, right? There is no additional metric. There is just one metric. And anyway, so this is general covariance. And the general covariance really is a mathematical expression of equivalence principle, which is the big insight that Einstein had in 1907. All right, it's consistent to special relativity, of course, right? Because special relativity is just a special metric, Lorentz metric, the Minkowski metric. You can recover Newtonian theory, right? Okay, that's a little bit harder to see, but you can do it by taking, there are various ways of getting Newtonian theory, in particular to taking the speed of light to go to infinity, but you need something more, but let me not say that, let me not do that. Predicts gravitational waves. So this is a remarkable thing about the Einstein equations. Unlike Newtonian gravity, when of course it's all based on action to distance, to any distance, here because of special relativity, because of relativity, you cannot have action to infinite distances as you have in Newtonian mechanics. And this leads to a prediction of gravitational waves that we will discuss in a second. I mean, that of course has something to do with the hyperbolic character of the equations. You have non-trivial solutions, so we'll talk more about this, but you have non-trivial solutions in vacuum. This simply means that in the Einstein equations, if you take the energy momentum tensor to be 0, then you get R alpha beta minus a half G alpha beta R is equal to 0. But then if you take a trace with respect to the metric, you get that the scalar curvature has to be 0. And therefore, you conclude that the Ricci tensor is actually 0. So these are the Einstein equations in vacuum, purely geometric, and they have non-trivial solutions. The remarkable thing is that they have non-trivial solutions which have nothing to do with matter anymore because there is no matter, and they can only be gravitational waves. So any non-trivial solution of this, dynamical non-trivial solution, has to be a gravitational wave. It's a quasi-linear system of hyperbolic equations, right? So I presume, again, that everybody knows what quasi-linear hyperbolic equations are, but we'll say more later. Anyway, it's a special type of nonlinear PDE system, but not unless you understand the so-called moduli space of solutions. So let me say something about this. Again, most people know, but let me still say it. So if you just write down, say, the vacuum equations, R mu nu is equal to 0, if you just write down in an arbitrary system of coordinates, you pick up an arbitrary system of coordinates, you write it down, you will get an awful-looking system of equations, second-order nonlinear, and which has no type whatsoever. Right? It's not elliptic, it's not hyperbolic, it's not parabolic, it's nothing. Right? It's terrible. It loses derivatives and so on and so forth. So it looks very bad. However, in doing this, you have to remember that there's nothing special about one system of coordinates. I mean, the equations are covariant. And therefore, the metric in a given system of coordinates, right? So if I look at the metric in a given system of coordinates, there's nothing special about it, right? I can change coordinates and get exactly the same thing. So in other words, if I take a map from M to M, and if I have a metric, then from a mathematical point of view, there is no distinction between G and phi star of G, right? So this is covariance again. The metric can look very differently in one system of coordinates than in another. But from a mathematical point of view, it doesn't matter. What this means is that I can choose coordinates to express this equation in a more favorable fashion. And of course, we all know about the so-called wave coordinates, which were first used by Yvon Choquet-Brouat to prove an existence result for the Einstein equation. So these are coordinates where you pick up the coordinates in such a way that the wave operator associated to the metric G applied to the coordinates is 0. And therefore, solving the Einstein equation in a PDE fashion such that I get something. Yeah, sorry, I should have said. Once you make this, then once you make this choice of coordinates, then these equations take a nicer form, and they start looking like wave equations. So d nu of G alpha beta is something nonlinear in G and derivative of G. So this will be, so you get a system of equation like this. And of course, I still have to remember that the derivation of G of x mu is equal to 0. Okay? So somehow you are solving not only the Einstein equations, but you are solving the Einstein equations together with a coordinate system. You find a coordinate system. Of course, this depends also on the metric, which you don't know. So this is also unknown. Anyway, so that's a kind of system where you recognize hyperbolicity. Hyperbolicity for the simple fact that this operator, if you were in Minkowski space, this will be m mu nu d nu of phi of G, let's say. But this is, in Minkowski space, this is just the wave operator, the standard with the wave operator, right? In other words, minus dt squared plus Laplacian. And therefore, this is a well-defined system of nonlinear hyperbolic equations, which you can study. So that's what moduli space of solution is, which means, of course, that in general relativity, the problem of coordinates is a fundamental problem. Whenever you want to write down a system of equations which has some character, elliptic, hyperbolic, you have to pick up some kind of gauge condition. Not necessarily coordinates, as we shall see, but some kind of gauge condition. Finally, another fundamental feature of the equations is they predict non-trivial solitons, and these are black holes. Okay, and that's what. Let's take a break and talk about black holes afterwards. All right. So maybe I should. We should stop. We should start again. So, again, I just want to, invite people to interrupt all the time. So this is supposed to be very informal, right? Now that there are fewer, it should be even easier to make it informal. So please ask questions and interrupt. So otherwise, I maybe tend to, as you saw in the first part, I didn't know how fast I should go. So I ended up by being indecisive. But I want to make it this as informal as possible, right? So if you want more explanations, please ask. Okay, anyway, so these are the main features of general relativity. General covariant, consistent to special relativity, Newtonian, predicts gravitational waves, non-trivial solutions in vacuum, quasi-linear hyperbolic equations, non-trivial solitons, right? Moduli space of solutions here simply means that somehow you have the impression, yeah, I should, obviously when you solve the Einstein equations, you have to find the metric that verifies this, right? So you think that the metric is a solution. In reality, it's not the metric, but the metric modulo the space of diffeomorphism, right? So you look at all possible pullbacks of the metric, and a solution is really a class of equivalence of metrics. Okay, black holes. Oops. Does it work? It does. No. This works only for this. Yes. Okay. All right. So now, okay. So explicit solutions. We go very fast. Of course, I'm only going to talk about explicit solutions for the vacuum equations for the moment, at least. So R mu nu is equal to 0. So we have, of course, the Minkowski space. We have Schwarzschild, which was discovered in 1916. It's static and spherically symmetric. We'll explain what that is later. The Kerr family, which is stationary axially symmetric, 1963. And of course, a lot of cosmological solutions when you include the cosmological constant, lambda, and you obviously can include matter. Okay, so these are the Einstein equations with a cosmological constant. Now, anyway, there are all these family of solutions, which I'm not going to talk about it. So I will talk mainly about solutions of the Einstein vacuum equations, right? And moreover, I'm going to assume I'm going to look at solutions which are asymptotically flat. In other words, solutions like Schwarzschild and Kerr, which become Minkowskian at very far distances. Okay, so asymptotically flat means that things look Minkowskian far away. Okay, we'll make it more precise later on. Okay, so let's go to the Minkowski space. So this is a, oops, what happened? Okay. Yeah. So that's a Minkowski metric, Minkowski space, coordinates. This is a point P, and this is a past of the point P, right? So that's how they look. And of course, this is a conformal compactification of Minkowski space. So conformal compactification, you'll hear a lot about it in what follows. So what this means is that I want to take this space and associate boundaries at infinity, so that the Minkowski space becomes compact, right? So it becomes something like this, so I can visualize it. And there is a specific way. By the way, I guess I didn't say, maybe I should mention it now, that there are various books for people who are interested and who want to learn more about general relativity. There is, of course, the beautiful there are beautiful lecture notes of Poincaré. I think this is also now in a book format, and it's, I think what is it called? It's just lecture notes in GR, which you can find it in the internet. I mean, you can just download it from the internet. There is, of course, Robert Wald, general relativity. And there is another book that I like, which is Inverno. There is the Inverno book which called Introducing Einstein Relativity. Introducing Einstein. So I'm going, of course, very fast on various issues which are developed for many pages in that book. Particularly the conformal compactification of Minkowski space, it's something that everybody should know. There is a very nice exposition of it in Wald, and I'm pretty sure that must be one in Carl's lecture notes. But anyway, the way to interpret this picture is that somehow there are these boundaries, which are boundaries at infinity. They represent endpoints of null geodesic. Everything null goes at 45 degrees because that means, for example, t is like absolute value of x, or t is like x1. So they're all at 45 degrees. And a geodesic here at 45 degrees should be viewed as something that ends up in the future boundary. This is called Scri plus, this is called Scri minus. So Scri plus are endpoints of null geodesics. There is, of course, this is expressed in polar coordinates. right? So you can, that's why you have the axis. So the volume element, the line element is expressed as minus dt squared plus dr squared plus r squared, the sigma squared, which is relative. This is the line element of the two-sphere. And therefore, this is the axis, r equal to 0. It looks like a boundary. Of course, it's not a boundary because you have to think about the fact that all this is rotated around r equal to 0. And you have I plus is viewed as a point. Of course, it's not a point. It represents an infinity of directions which are time-like. So all time-like directions end up at this point in this picture. And any space-like curve ends up here at I naught. Okay? So that's how you should view. R equal constant is represented by these lines, which are time-like. So any questions about it? So that's what the Minkowski space looks like in conformal compactification. Of course, here there is another picture of Minkowski space. Null geodesics at 45 degrees. These are straight lines which are generators of the light comes from points. There is a space like hypersurfaces or are represented by this, right? This will be like t equal constant. This represents an accelerating observer. It's time-like, but it's not straight. Geodesics have to be straight, of course, in Minkowski space. And so on and so forth. This is a time-like hypersurface, and so on. OK, so this is now Schwarzschild. So the Schwarzschild metric, it's another explicit solution, now highly non-trivial now. It has a name here. If m is equal to 0, you get just Minkowski space, right? So this is a modification of Minkowski space, but a non-trivial modification because you have singularity at r equal to 2m and r equal to 0. Now, r equal to 2m is not a singularity, as it's well known. In fact, it represents in this picture, which is a complete picture of Schwarzschild. Again, it's a complete picture of Schwarzschild. R equal to 2m are exactly these boundaries, right? And if you look in the original coordinates, which are these ones, you see that r equal to 2m seems to be a singularity, but it's only a singularity because of the system of coordinates you pick. If you change coordinates, you see that, in fact, this is nothing bad happens here. It's called a horizon, but it's a boundary between the region which looks Minkowskian far away, right? I mean, obviously, if r goes to infinity, you get the Minkowski metric, right? It looks more and more like Minkowski metric for r going to infinity. But for r close to 2m, the behavior becomes very different. At r equal to 2m, you have a boundary, you have a transition between this region here, colored like this, and the black region, which corresponds to a black hole. Once you are in a black hole, what is characteristic about black holes is that any time-like or null geodesic cannot escape, right? Anything which is parallel to this will have to stay in this region, so you will never escape a black hole. Once you are inside, you never escape, and moreover, you will reach a singularity in finite time. So the r equal to 0 is a true singularity. You can show that at r equal to 0, all scalar, all interesting scalar curvature, I mean scalar invariants based on curvature blow up. OK, so this is how it looks. Now, once you pass in this region, you can actually keep continuing, and you get another region which looks very much like this one. And also you get something symmetric to this black hole region, which is called the white hole region, which is physically not very interesting because, in principle, such things don't occur naturally. But anyway, in the picture of the Schwarzschild spacetime, the maximal extension of Schwarzschild, you have to take into account all these regions. Questions? Am I going too fast? Everybody knows. OK. So this is now the Penrose diagram, so including the conformal compactification, where you see these boundaries, which are like in Minkowski space, in fact. So they are constructed very much like in Minkowski space. And again, you see the 4 regions, the black hole, the white hole, and the 2 exteriors, right? This one is completely symmetric to this one. The vector field d over dt is, of course, the partial derivative with respect to the t component in these coordinates, and is a Killing vector field in the sense that the metric is independent of t. The coefficients of the metric are independent of t. D over dt is also hypersurface orthogonal. You can see that it's orthogonal to the hypersurface t equal constant, okay? Which makes it a static metric, right? So static means exactly this, that the Killing vector field, so Killing vector field means, well, we'll make it more precise in a second. This is a Killing vector field, and it's hypersurface orthogonal. Right? You can also see that the metric is static, because if you change t to minus t, you get the same thing. So there is a symmetry with respect to t. From taking t to minus t, you get the same form of the metric, right? There are all sorts of interesting regions which play a major role in the analysis of Schwarzschild solutions. For example, R equals 3m. So R equals 3m, right? These are, when R is equal to 3m, you get a hypersurface which is time-like and which contains null geodesics which are tangent to it. And these will be null geodesics which are trapped, so-called trapped null geodesics on R equals 3m, which lead to a tremendous number of problems in the analysis of these solutions. Okay. Another interesting feature of Schwarzschild is that the vector field d over dt becomes null on R equal to 2m. In other words, on the horizon. And you see it in the picture that this light cone is tangent here on the event horizon. This is called the event horizon, R equal to 2m. So the boundary of the exterior region. What else shall I say? Yeah, and of course you see that in the interior, the null cone, the d over dt is in the interior of the light cone, which means that d over dt is actually time-like. So everywhere in this region, the vector field d over dt, which is this important Killing vector field, is time-like, but it becomes null here. Once you pass the horizon and you go inside here, d over dt actually becomes space-like. Right? So it completely changes the character of the. Sorry? No. Well, it doesn't make sense to talk about it. It still has a symmetry, right, relative to t. But you know, notion of static makes sense only in the exterior region, right? Okay. Yeah. Is that okay? Yeah. All right. So again, stationary axisymmetric, event horizon R equal to 2m, black and white hole regions, R is less than 2m. Exterior domains, these ones, R is larger than 2m. The so-called photons here, when R is equal to 3m, will obviously encounter it later on. Okay? So there is future null infinity is complete. I'll explain it in a second what that means. There are no naked singularities and no Cauchy horizons. Okay, so let me explain at least these two things. So the fact that we say that this future null infinity is complete because if you perform this conformal compactification, this is going to be a null hypersurface. The boundary is going to be a null hypersurface. Right? Null hypersurfaces are generated by null geodesic vector fields. And if you look at the affine parameter relative to this null geodesic vector field, the generators, this looks infinite. So this going from here to here takes an infinite time relative to the affine parameter. In particular, it means that somehow there are no singularities along here, right? So if a singularity will happen somewhere in the interior, for example, if for some reason something becomes bad here, then the singularity will propagate and will affect what happens at the boundary. We'll talk about this maybe later on. But in any case, there are no naked singularity means exactly the fact that the future non-infinity is complete, and therefore nothing inside can be a singularity. Of course, we know a priori that there are no singularities. If you look at the form of the metric, the only singularities occur at r equal to 0, which is inside the black hole. Here, everything is smooth, right? Okay, but we'll see these pictures coming later. Okay, now Kerr, another explicit solution that's a complete family now, involving two parameters. When a is equal to 0, you get a Schwarzschild metric. But this family is interesting for all a's between 0 and m. Actually, a can be between minus m and m, in fact, but by symmetry, you can just look at a larger than 0. Okay, so this is the form of the metric now is more complicated. There is no point in getting all the, I mean, if you haven't seen the metric, there is no point in trying to absorb everything here. The important thing is that it's explicit. It's an explicit form. It's an explicit metric. Everything is explicit in terms of trigonometric functions, right? It may look complicated, but it's amazingly simple if you think about what it represents. So this is the most important explicit solution in all of general relativity. And probably it's the most important, the most amazing explicit solution in all of physics, in my opinion, because I don't think there is any part of physics where you have such a two-body problem in Newtonian mechanics, of course, is an example of a highly non-trivial explicit solution of the equations, of a nonlinear equation, right? Because Einstein equations are nonlinear, so it's very hard to write down solutions. This is an explicit solution, and it's remarkably simple, and it represents physical phenomena. I mean, it represents serious physical phenomena. All the theory of black holes that we have is based on these solutions. And maybe generalization of these solutions when you add another parameter here, which is E. But this corresponds to the Einstein equations, not in vacuum, but in, when it's coupled with electromagnetic field. Okay? So anyway, it's an amazing solution. It's asymptotically flat. It's easy to see that, again, when r goes to infinity, it's, of course, it's expressed in terms of r. By the way, when a is equal to 0, it's easy to see that you get the Schwarzschild solution. When r goes to infinity, of course, you get the Minkowski metric. It's also very easy to see. So it is asymptotically flat. It represents an isolated system. That's why it's so important in modeling physical phenomena such as collapsing stars or you know, black holes, big black holes in the center of galaxies, and so on and so forth. Right? Okay, so this is our main object, in a sense, in the theory of black holes. Okay, this is the maximal extension of the Kerr solution. So you want to do something similar as you did for Schwarzschild, right? Again, you get 4 regions. You get this region also. You get 4 regions, just like in Schwarzschild. The boundaries now are r equal r plus. So this boundary was what was before the event horizon. It was r equal to 2m. Now r plus is in fact a solution of this equation delta of r plus, where delta is just r squared plus a squared minus 2m or 2mr. So of course, when I equals 0, you get r equal to 2m. But now you get a different value, but you know, you just calculate. Again, you have so the exterior region, you have a boundary at infinity, very similar to Schwarzschild. So this region is very similar to the Schwarzschild region. The only big difference occurs inside, where you don't see anymore r equal to 0 as a singularity, but instead you see r equal r minus, which is another root, the smaller root of this polynomial. This polynomial has 2 roots. r plus corresponding to this, r minus corresponding to this. R minus is a smaller root. And this has now a new meaning. This is actually now Cauchy horizon, in the sense that if I start up with a space-like hypersurface here, right, which is a Cauchy hypersurface for the region under interest, if you look at the boundary of the domain of dependence of this Cauchy hypersurface, you now get these regions also. So somehow space-time terminates at the region r equal r minus in the future of this hypersurface, where r minus is not a singularity. So nothing bad happens here, right? The curvature actually can be the curvature makes sense, and the metric can in fact be extended. But by extending the metric, you can have infinitely many extensions beyond this r equal r minus. And then, of course, you have a very serious problem that somehow the extensions have nothing to do with the initial data. And of course, this will violate the principle of determinism, which is fundamental in all of physics, in particular to classical theories like general relativity, where somehow a solution should be completely determined by initial conditions. So the knowledge of the solution here on this hypersurface should determine all the future development. I mean, in other words, all points which are causally related to this. But these points here are not causally related anymore, and therefore somehow it means that there are regions of space-time which are not at all influenced by the initial data. Right? So that's strange. I mean, that's bad. Okay, so the maximal global hyperbolic development, I didn't yet define. We'll discuss it in a second. Terminates at the Cauchy horizon r equal r minus. Even though this maximal global hyperbolic development, which maximal global hyperbolic development means all this region, even though it remains smooth. Now, there are no singularities in this region. Thus, there are many possible extensions beyond equal r minus contradicting determinism. Okay, so that's exactly what I said. Now, yes. Yeah, you can make extensions that solve the Einstein equations also. Yeah, sure. You can do all sorts of things there. Yeah, true. So the hope is that and this is one of the conjectures I'll talk about, the hope is that sorry, I should go before. So the hope is that this r equal r minus is in some sense unstable, right? So in other words, it's an artifact of the symmetry of the Kerr solution. And if you make small perturbations, it shouldn't be there. Anne knows more about this. So maybe she can tell us more at some point. Okay. Right, so this is just the external region. And for most of my lectures, I'll talk about external regions of black holes. Okay, so now here is the interesting thing about the Kerr solution in the exterior. It also has a killing vector field, which is also d over dt in the so-called Boyer-Lindquist coordinates. Boyer-Lindquist coordinates are just the coordinates that you see here, right? T, R, and phi, which makes sense in the exterior region, makes perfect sense in the exterior region. If you want to extend it beyond, in other words, if you want to go beyond this boundary, so it makes sense up to these boundaries. If you want to go beyond these boundaries, you have to change coordinates, but that can easily be done, and then you get these regions and these regions and so on. But you observe that all the coefficients of the metric are time independent. They don't depend on dt. In other words, the vector field d over dt is a Koenig vector field, right? We say. So these solutions are also stationary, right? Because they don't depend on time in this simple, exact, precise form. Okay. Now, obviously, the vector field capital T, which is this d over dt, is a very important vector field. Koenig vector fields are always important in general relativity. And what can we say about them? Well, first of all, in far away, so again, you can have, of course, a conformal compactification just like in Schwarzschild. So far away from the event horizon, this is the event horizon, r equal r plus. So far away from this region, d over dt looks time-like. Looks just like in Minkowski space, right? In fact, when r goes to infinity, you get Minkowski space here. So this region looks very much like Minkowski space, and the d over dt looks very much, like it should be perpendicular to d over dt directions, right? So it should look like this. So it's vertical. However, as you approach the event horizon, which is this one, there is, at some point, there is a switch. D over dt becomes space-like instead of being time-like. And of course, this is different from Schwarzschild. In Schwarzschild, d over dt became null, but it was time-like everywhere in the exterior. It becomes null only on the horizon, and then, of course, becomes space-like inside. But here, this phenomenon occurs earlier in what is called the ergosphere, the ergo region. So there is an ergo region where the vector field actually becomes space-like. And that leads to all sorts of problems, right? So all sorts of analytic and physical problems. OK. So this is stationary axis symmetric, right? So it's not static anymore. So why is it not static? Well, it's very easy, because if you look at the form of the metric, if you now change t to minus t, right, you get a problem, right? So it's not symmetric relative to d over dt. And it's easy to see that d over dt cannot be hypersurface orthogonal. It is axis symmetric because the metric has another Killing vector field, which is very easy to read in these coordinates. It's just d over d phi. So that d over d phi is a Killing vector field also, right? Which corresponds to a rotation. So this is a black hole, a rotating black hole. Right? Unlike Schwarzschild, which was spherically symmetric, there was no rotation. So that's why these Kerr solutions are so fundamental in all of general relativity, in fact, in astrophysics, in all of physics. OK, so what are the key properties of the Kerr spacetimes? Let's review now. Well, first of all, there are solutions of the Einstein vacuum equations, right? That's a very important one. Second, they are stationary. In other words, there exists a Killing vector field T, which is d over dt in the standard coordinates, in the Boyer-Lindquist coordinates, which is time-like at infinity, but not necessarily time-like everywhere in the exterior region, right? So in the region outside the black hole, this can become, in fact, space-like. So that's happening in the ergo region. The other geometric properties, asymptotic flatness, they are asymptotically flat, they are smooth, right? Smooth, again, in the exterior region, but even in the interior region, we know now that they are smooth. But the exterior is what we care about. So again, exterior means all the way up to the horizon, up to r equal r minus. There is a bifurcate sphere that means non-degenerate if if is different from m. So this is, maybe I should rephrase it in saying that they are non-degenerate if A is strictly less than m. And there is a degeneracy at A equal to m. These are called extremal black holes. And of course, physicists and mathematicians talk a lot about extremal black holes. Anyway, asymptotic flatness, smooth solution, bifurcate sphere, that means non-degeneracy, and global hyperbolicity. They are globally hyperbolic, as you can see from this picture, right? Well, yeah, this part is globally hyperbolic, right? Every point here, if you look at any time-like curve passing through a point, it will intersect, for example, this hypersurface at one point. Okay? So it's globally hyperbolic. Okay. Okay, so this is a repetition, non-degenerate. Algebraically special. Okay, so what does that mean? This is something I'm not going to get into it. You see, the Riemann curvature tensor has 20 components. And 18 of those vanish if you find a suitable frame. So relative to a suitable frame, there are only 2 components left. Okay? So that's very important. Okay, but I mean, it will be very important, and we'll discuss it later on. Okay, so it has a killing vector field. So in addition to this, it has another killing vector field, which is d over d phi. And d over d phi, of course, has closed orbits, right, which corresponds to axis symmetry. All right. Any questions? Finally, the metric is specific. It's also real analytic. Of course, it's even more than real analytic. It's trigonometric, algebraic, trigonometric, whatever you want, right? So it's clearly a very special, I mean, in particular, it's real analytic. Okay, so now we will study later on, we are going to discuss more general spacetimes which satisfy the condition P0, P1, P2, P3. Okay? And these are called regular non-degenerate stationary vacuum. In other words, imagine that you have solutions of the Einstein equations, which are not necessarily Kerr and not necessarily Schwarzschild. They are still vacuum equations. They are asymptotically flat. They verify all the conditions that you see here. They are stationary in the sense that there exists such a vector field. They are asymptotically flat. They are smooth. They have bifurcate sphere, whatever that means. Well, actually, it's easy to see what it means. Maybe I should show it. See, bifurcate sphere here. There is a future event horizon and a past event horizon, and they intersect transversally at some point. Okay. Now, this is a situation when A is different from M. And when A is equal to M, this picture is incorrect. Okay? Right. So that's... okay, so that's... okay, so what are the mathematical questions connected with these black holes? It's not hard to see. First one, the first obvious one is, are there any other regular stationary vacuum solution besides the Kerr family? Right? It's a very fair question. I mean, are there others? Right? That's called the rigidity problem. So the conjecture is that there are none. Right? So in other words, the Kerr family, based on these two parameters, really identify all possible stationary solutions which are reasonable. I mean, in other words, regular stationary solutions. Right? So. Okay, so that's one question. Then the obvious next question, which is in a sense even more fundamental, but it's clearly tied to this. Right? You have to understand this first, but then next you want to understand this. Are the space-time, the Kerr family, stable under general perturbations? Okay, so I'll talk a lot more about this in a second, but it's obviously what it means, right? If somehow a small perturbation will destroy the Kerr family. I mean, if I start up with something which is close to Kerr, and then the evolution will be such that I get something far away from Kerr, then of course the very notion of a black hole as an astrophysical object will be false, right? So whenever people talk about black holes as being, I don't know, all over the cosmos, there is an implicit understanding that these spacetimes are stable, right? Of course, proving it's a different story, and it's this other one is also very relevant because whenever they talk about black holes, they always refer to these parameters, A and M. So they always identify whatever black hole they see as being a Kerr black hole, or maybe a Kerr-Newman, but certainly typically a Kerr black hole, right? So they assume that indeed there are no other stationary solutions outside the Kerr solutions, right? Okay, another kind of questions you can ask are the singularities present in this explicit solution stable? In particular, Schwarzschild, is the R equals 0 solution stable? It's a big question. In the case of Kerr, of course, we don't have singularities, at least insofar as the picture that we saw. But you can ask whether this R equal R minus, which was the Cauchy horizon, you can ask whether the Cauchy horizon is stable, right? Okay. Okay, another one is are singularities for general solutions also covered by an event horizon? So this is the so-called cosmic censorship, which I'll talk about in a second. So let me go to the next slide. What time? How much time I have? Where is it? Okay, so I still have enough time. Okay. All right, so let's, before talking about the cosmic censorship conjectures, which are sort of the most obvious open questions in general relativity, let me talk a little bit about Penrose singularity theorem, because I think that gives you a lot of intuition. So this is a beautiful, very simple result proved by Penrose in the 1960s. And then Hawking also had some variations of it. But Penrose's original result, I think, is the one that we always sort of refer to. So it's a singularity theorem. People say it's a singularity theorem. In fact, it's an incompleteness theorem. It's not a singularity. It's something about geodesically incomplete space-time. So the statement, in fact, is like this. A space-time mg cannot be future null geodesically complete. I'll explain it in a second. If certain hypotheses are satisfied. So there are three hypotheses. First of all, think of L as being a null vector field, right? I mean, this is a pointwise condition. At every point, you have a vector field which is null. So null means it's at 45 degrees as before, right? Null simply means that GLL. So if you have a spacetime mg, L is null if simply if GLL is 0. Right? So you take any such null, then the Ricci applied to it has to be larger or equal to 0. Of course, this is automatically satisfied if you have the Einstein vacuum equations, because in that case, Ricci is just 0, right? So, but the condition is much more general, and it's of interest for spacetimes which have matter, and the matter verifies a very natural positive energy condition, right? So anyway, so this is a very natural, extremely natural condition. Has a non-compact Cauchy hypersurface. In other words, the spacetime mg has a non-compact Cauchy hypersurface. Cauchy hypersurface, we know what it means. It's something that it's very natural, right? And you want it to be non-compact, right? So of course there will be spacetimes which are spatially compact, but asymptotically flat spacetime, of course, enter in this category. They have non-compact Cauchy hypersurface, right? So this is again a very natural condition for asymptotically flat manifolds. The only non-trivial condition is this one. There exists a closed trap surface. So let me try to explain now what a closed trap surface is. All right, so this is a two surface. We are in 4 dimensions. This is a space-like surface. So in other words, it's called dimension 2, and it has a topology of the sphere, right? So it's a compact thing, right? So in Minkowski space, it's very easy to visualize. So let's look at the Minkowski space. So in Minkowski space, you have a hypersurface. Let's take it to be a sphere, in fact, to start with. Right? So in other words, this is a standard sphere in Minkowski space. And you can then look at null cons generated by outgoing directions. Outgoing directions simply means you go away from this region, from the inside of the sphere. Right? And you can also have incoming null cons, which are going this way. Okay? Okay, so that's a very natural picture in Minkowski space. As you can see, the incoming ones are such that well, maybe, I mean, my picture is not very accurate at all, but anyway, like this. Right, so this is, you start with here. And if you move along these directions, the area of the two surfaces, so in other words, if you vary the original surface along these directions, the area is clearly decreasing, right? In fact, it's very easy to see that it's decreasing at every point, right? So you can talk about infinitesimal change of the volume of the area element of the sphere, and you can see that the areas are decreasing, while of course the areas are increasing along these directions, right? Okay, so in other words, the so-called incoming ones, at every point, of course, I have two null directions, and which are perpendicular. So if you want to make it more formal, you take two null directions which are perpendicular on these two surfaces. Right? At every point on the surface, I definitely have such two things. Right? And then you look at the variations of the area along this and the variations of the area along this. And of course, you see that things are increasing here and decreasing here. And that's a general situation. Now, you could have, in Minkowski space, you can have a slightly more complicated situation. You can have something like this. Okay? In other words, you have a dent in your surface. So instead of being convex everywhere, it's now concave. And therefore, if you look at the null geodesics now in these directions, the outgoing ones will be also decreasing. Will be decreasing, despite the fact that at every other point, things will, of course, the areas will be increasing, right? So, so in other words, whatever corresponds to these directions are typically, the area element is decreasing at every point, except maybe in regions where you have concavity instead of convexity, right? That's a very natural. Now, you can never have, however, a situation like here, which is called the trap surface, in which at every point on the surface, you have both the incoming and the outgoing null geodesics, right? This will be null geodesics generated by points on the surface. Along them, the areas are both. So on a trap surface, what happens is that if I look at both directions, right, which corresponds to what I said earlier in Minkowski space, if I look at both directions, in both directions I get that the areas are decreasing at every point on the surface, right? So this is a definition of a trap surface. So on a trap surface, something very dramatic happens, which is impossible to reproduce in Minkowski space. You can never have in Minkowski space a trap surface, right? However, this condition, this trapping, is always true if you look at black holes. So if you are in a black hole, let's say here, let's say for a Kerr solution, every point here inside the black hole, every point is a 2 surface, which is trapped. So everything here is trapped. The same thing in Schwarzschild. Every point represents a trap surface, right? Because, I mean, you are doing something which is 4-dimensional, we represent it in 2 dimensions. So every point here has, in fact, 2 dimensions. Every point corresponds to a 2-dimensional surface. And everything here is trapped. While, of course, here, everything here is non-trapped. So if you, in the exterior region, you cannot have trapped surfaces. It's relatively easy to see if you are in the particular case of Kerr or Schwarzschild. But here you have plenty, right, of surfaces which are trapped. So there are plenty, in other words, plenty of examples, but of course they have to correspond to a strong gravitational field, right? The Riemann curvature tensor here is very big, while it goes to 0 outside the black hole. So so that's a kind of extreme situation which you assume to hold in the Penrose singularity theorem. There exists a closed surface which is trapped, okay, completely trapped. In this, if all these conditions are satisfied, then the spacetime cannot be future geodesically complete. What does it mean? Of course, completeness in Riemannian geometry simply means, you all know what completeness means in Riemannian geometry. It simply means that all geodesics can be extended. So on a complete Riemannian manifold, right? If this is Riemannian, all geodesics in it can be unique, can be continued indefinitely relative to their affine parameter. So relative to an affine parameter, any geodesic can be continued indefinitely, right? So this is always the case of a sphere, for example. The geodesics can be extended indefinitely. Torus, whatever. I mean, all the important surfaces, of course, are complete. So this result tells you that you cannot, once you have a trapped surface, you cannot be complete in the sense that there must exist geodesics which are null geodesics, such that relative to the affine parameter, the geodesic has to terminate in finite time, in finite affine parameter time, right? Okay, so that's a very drastic thing that can happen if you have trapped surfaces. And of course, if you have a trapped surface, you expect to have a singularity. I mean, obviously, we know in Schwarzschild that there are plenty of trapped surfaces, and you have a singularity. Now, it's not true in Kerr, right? But that's because of this other effect, which is the fact that you have a Cauchy horizon. So is it contradictory what I'm saying? Yeah, so right. Anyway, take the example, right? So you have to be a little bit more careful with Kerr, but take the example of Schwarzschild. So in Schwarzschild, you have plenty of trapped surfaces. So every point in the black hole region represents a trapped surface, and of course you have a singularity at r equal to 0, right? So that should be the right example. Okay, so you can make these kind of things precise by introducing, in other words, the definition of trapping. You can make precise by introducing two fundamental quantities, which are extremely important in general relativity. So let me explain what they are. So you see, okay, so let's look again at the picture here. So you have a two surface, S. At every point, since I'm in 1 + 3 dimensions, I can find two null vector fields which are perpendicular to S, right? So one I'm going to call L, and the other is called L bar. So if S sits on an asymptotically flat manifold, in other words, there is a direction relative to which you go to infinity, then I can talk about one of them as being outgoing and the other one incoming, right? But it doesn't really matter. The important thing is that I have two vector fields, L and L bar. So for each one of them, I define the so-called null second fundamental form, so chi, which is defined to be the covariant derivative of L in the direction of y. So you have the metric. You take covariant derivative relative to a vector field x, L, y. So this defines a second fundamental form, just like in Riemannian geometry. In Riemannian geometry, if I give you a hypersurface, I can define the second fundamental form. Okay, so I can define the same thing here. And of course, I can define two of them because I have two vector fields, L and L bar. Right? So recall that both L and L bar are perpendicular to S. Right? So perpendicular to any vector field which is tangent to S. And in fact, x and y are taken here to be in the tangent space of S. Right? So let's call it like this. So they are vector fields in the tangent space of S. And I define these two things. Very much like in Riemannian geometry, if I have a space-like hypersurface and a normal, nu, then I can define the second fundamental form, k of xy, in the same manner by taking the covariant derivative of the metric of the normal in the direction of the vector fields. Okay, so these are null second fundamental forms. So these are tensors defined on S, and there are two tensors, as you can see, because there are two entries. So relative to a frame, if I introduce a frame here, EA, which is E1, E2, right? So A runs from 1 to 2. right? So if I introduce an orthonormal, I can take an orthonormal frame here. Then I can, relative to the components of the frame, I have chi AB and chi bar AB. Right? Okay. And then I can take now GAB, I can take the trace GAB. So of course, GAB is the induced metric, the metric induced by the space-time metric on S. Right? So I can take the trace, it calls this trace chi and this trace chi bar. So these two things are extremely important, they come up all the time. So I'm sure that most of you know already, but that's how you define the so-called expansion. So theta is trace chi, theta bar is trace chi bar. So the condition, which is equivalent to this one, is that there exists a surface S such that at every point on S, both relative to L and del bar, so you have two directions which are null and orthogonal to S, and future directed, right? You can also imagine a direction of time, and you can take both of them to be in the future direction. You can define this trace chi bar just as I did, and then you are asking that both of them are negative at every point, and you can take it to be strictly negative, right? So strictly negative, you definitely must have a singularity, right? And again, examples, there are plenty of examples because in Schwarzschild, any point in the black hole region has to be a Trapp surface. So this was an amazing result at the time because people were still debating whether the singularity R equal to 0 Schwarzschild was a true singularity or was an artifact of the fact that you have very symmetric solutions, right? So solutions with lots of symmetries, right? Particular static and spherically symmetric. So you could argue that maybe if you perturb a little bit, then that will disappear, right? The singularity will disappear, and in fact there are no singularities, and people prefer that there are no singularities for obvious reasons, right? Physicists, of course, having singularities is better for them because then they can start talking about quantum field theory, right? Quantum gravity. But in any case, the result of Penrose tells you that, in fact, because you have so many Trapp surfaces in the interior region, in the black hole region of Schwarzschild, they have to be stable because the condition of Penrose is a stable condition. It just tells you that something is strictly negative at every point. If I perturb it a little bit, it's still going to be strictly negative. And therefore, this tells you that the Schwarzschild singularity is actually a stable singularity, right? And it's not an artifact of the symmetry. So that's why it was so influential, the result of Penrose. It's again not a singularity theorem because you know it doesn't give you nothing blows up. It's just an incompleteness result, but nobody has been able yet to prove. Anyway, the proof is actually very simple, and I just want to sketch it. Again, you find it in lots of books. But I just want to convince you that the ideas are extremely simple. I mean, the main ideas are trivial. Well, not trivial, but very, very simple. They actually involve relatively little from the Einstein equations. So in fact, it turns out that the only thing of the Einstein equation which is used, okay, so again, you have this trace chi and trace chi bar corresponding to L and L bar. So the L bar direction is incoming, and therefore you expect things to be negative anyway. So you can forget about this one. The important thing is to look at the outgoing ones, right? So this corresponds to this direction, L, which in Minkowski space, this will go like this, but because you are trapped, you go inside still. So intuitively, it looks like you should have a singularity, right? Because this obviously, you know, anyway, cannot prove anything just by drawing pictures, of course, but you can expect that something bad is going to happen. But the true proof goes like this. You show the trace chi, right, which we have defined. So the trace chi corresponding to this one verifies an ordinary differential equation, which is d over ds. S is an affine parameter of the geodesic. So this is a geodesic curve, and you take the affine parameter along it. And relative to that affine parameter, you find this very simple equation, which is called the Raychaudhuri equation. It's a fundamental equation in general relativity. And it's a simple consequence of the Einstein equations. Actually, this is not even the Einstein, sorry. This is not even the Einstein equation. This is the general fact. Take d over ds of trace chi plus a half trace chi squared. So this is a nonlinear term, is equal to minus chi hat. So what is chi hat? I have to define this also. So we have the null second fundamental form. We have trace chi, which is also called theta. Physicists usually call it theta. It's called the expansion. And you subtract from it. So you take chi minus a half trace chi times the metric, the induced metric. So let's call it, I still call it G, but you have to think about it as being the induced metric on S. Right? So this is still a 2 tensor. Right? So I have chi AB. And this is G AB. And this is what you call chi hat. So it's a traceless part. In other words, you took away the trace. Right? So that's a traceless part of the tensor chi. So you have this term here, but you see it comes up with a good sign. It's minus. And then if the Ricci here is also positive, it means this is also a minus. So all this thing here is a minus. So you have d over ds trace chi plus a half trace chi squared is negative. And this equation, of course, is a Riccati type equation with a negative right-hand side. Everybody, yeah, you just look at this equation. D over, well, let me write it like this. It's even more obvious. X dot t plus a half x squared is negative. And you look for t positive. It's very easy to see that it will form a singularity in finite time. So you get a singularity in finite time. And this is the main reason why you have this incompleteness theorem, because then you combine this observation with a simple topological argument which tells you that if I look at the future of S, from here I conclude that the future of S has to be compact. On the other hand, it's very easy to show that there exists a diffeomorphism from the future, sorry, this is the boundary of the future, excuse me. So I look at S, I look at the future of S, I take its boundary. The boundary has to be compact because of this argument. And then I can easily establish a homeomorphism between the boundary and sigma 0. Sigma 0, remember, sigma 0 was this Cauchy hypersurface that I have to start with, right? So this was the assumption that there is a non-compact Cauchy hypersurface. So there is this diffeomorphism, but now you reach a contradiction because sigma 0 is non-compact and the future is compact. So contradiction, and you declare victory, right? So that's all that is to this result of Penrose, but it was a very influential result. Okay, so questions. Obvious question. Well, what is the significance of this uniformity condition? I mean, it's very hard to imagine that this happens naturally, that you get a trap surface. How do you get a trap surface? It's a very extreme condition, which is pointwise at all points. Now, anybody who knows hyperbolic equations, you know that in hyperbolic equations, you work usually with average quantity, L2, and so on, L2 estimates. It's very hard to get anything which is pointwise, right? So anyway, so this is a big question. So as a consequence, the natural question that you have is, can trap surfaces form in evolution? Can you form a trap surface in evolution? Right? Can you form it in vacuum? So the condition of trapping is now becomes the fundamental thing. You want to show that this trapping occurs naturally. You start up with initial data where there is no trapping involved, and somehow later on in the evolution you get trapping. And finally, you want to get a quantitative version of the incompleteness theorem. In other words, can you actually get actually a singularity, not just incompleteness, but a true singularity, a true curvature singularity? All right, now how much time I have? I guess 0 time, right? Okay. All right, so again, am I going it the right way now, or is it still too fast, still too slow? Yeah? Well, let's see. How many people think that I am going too slow? Okay. How many people think that I'm going too fast? One, I'm going too fast, and one, I'm going too slow. Sorry?
I like it slow.
Slower. But is it like, okay, so you want slower than I did? Right. Okay. So you see what I'm doing now is just try to give you a big overview of the subject, and then I'll get into something more concrete, right? So we'll talk about the initial value problem, the initial value formulation. Then I'll talk about the cosmic censorship conjectures, and then various topics of interest in mathematical general relativity. What are the problems? What can be solved? What has been solved? And so on. So probably it will take me another 2 hours to give this introductory lecture. So next time I'll give another 2 hours about. I'll follow this with this notes which I have here. Okay, so